Hello. Today we're going to talk about refraction. We'll start by talking about what refraction is and define the refractive index. Then we'll do some calculations using Snell's law. And finally we'll talk about the concept of internal reflection. Refraction is a property of waves. When a wave moves from one medium into another, it can change direction, and we call this changing direction refraction. We're primarily today going to talk about refraction in the context of light, though it is worth mentioning that other types of wave can refract as well. The way that we quantify refraction is with the refractive index n. It's quite simply the ratio between the speed of light in a vacuum and the speed of light in a particular medium, for example glass or water. It's also worth noting that the speed of light in a vacuum is very, very close to the speed of light in air. In fact, we often say that the speed of light in a vacuum is equal to the speed of light in air. Here's a question for you to have a go at yourselves. Pause the video and write down the answer to the following question. My answer, as well as my working out, will follow shortly. Firstly, we should note that the refractive index is equal to the speed of light in a vacuum divided by the speed of light in a medium. We should also note that the speed of light in a vacuum is very approximately equal to the speed of light in air. V is the speed of light in this fibre, which is the medium, and therefore V is 3/5 of c. Putting this into our equation for the refractive index, we get that n is equal to 1.67, meaning that the final answer should have been D. When light moves from one medium to another, it will change direction. That is, it will refract. We can measure refraction using Snell's law. We say that n1 sine theta 1 is equal to n2 sine theta 2, where n1 is the refractive index of the original medium and n2 is the refractive index of the medium the light enters. Then theta 1 is the angle of incidence and theta 2 is the angle of refraction. It's also worth noting that the refractive index in a vacuum is equal to 1 and the refractive index of air is very, very close to 1. Let's consider the example on the right, where light travels from air into glass. In such a case, the incident ray will enter the glass at an angle and it will be refracted towards the normal. The angle of incidence, theta 1, will be greater than the angle of refraction, theta 2. When the light leaves on the opposite side, the opposite thing will happen and the light will bend away from the normal. It will also be parallel to the original incident ray. It's very important that you can use this equation for yourself, so pause the video and have a go at the question shown. I'll work through the answers in a few moments. Okay, so you should have noticed that n1 is equal to 1, theta 1 is equal to 56 degrees, and theta 2 is equal to 30 degrees. Therefore, putting these numbers into the equation, you should have worked out that the refractive index of glass is equal to 1.7. Finally today, we're going to cover internal reflection. Sometimes at a boundary, instead of being refracted, light can be internally reflected. In order for this to happen, two conditions must be met. Firstly, the light must travel from a higher refractive index to a lower refractive index medium. Secondly, the light must strike the boundary at an angle greater than a special angle called the critical angle. It's fairly easy to show what this critical angle must be. Firstly, we'll note that the critical angle occurs when the refracted ray is refracted through 90 degrees. At this point, we say that theta 1 is equal to theta c, the critical angle, and theta 2 is equal to 90 degrees. We should also note that sine 90 is equal to 1. Therefore, n1 sine theta c is equal to n2, and if we rearrange a little bit, sine theta c is equal to n2 divided by n1.